So when we can calculate the binding energy of a nucleus by just doing the process that we essentially just did, or we could calculate that binding energy by finding the missing mass. That's one thing that I didn't ask you guys to do in your problems, I don't believe. But another very interesting value would then be the binding energy per nucleon. And so we can calculate that by just dividing by the total number of nucleons, right? So the greater the binding energy in a nucleus, the more stable the nucleus will be. The harder it is to break the nucleus up. Likewise, we can calculate the binding energy per nucleon to compare nuclei to one another, which will become important in just a minute, as you will see. So if one atom has more binding energy per nucleon than another atom, then that nuclei is going to be more stable. It's going to be harder to break apart. The binding energy per nucleon is just calculated by dividing by the total binding energy by the total number of nucleons. So in the last example, we had neon 20. Neon 20 has 20 nucleons. And so the binding energy per nucleon, we would just take the given binding energy and divide by 20. 8 mega electron volts, or 8.05 mega electron volts as a binding energy per nucleon, is relatively high. Neon is a relatively stable nucleus. It's a noble gas. As you will see, they are not all that large. So we can do a very similar thing with the previous problem. You just have to pay attention to the words here. The binding energy per nucleon in the chlorine nucleus that we're given here is 8.57 mega electron volts. What's the atomic mass? Well, the first thing that we need is the total binding energy. And so we need to take 8.57 and we're going to multiply it. I'm sorry, unit converting here when I shouldn't be. We're going to multiply by the number of nucleons. So there are 37. And that gives us the total binding energy of 317.09 mega electron volts. Now the process is the same as before. We have 17 protons. We have 37 minus 17, or 20 neutrons. If we multiply those two values and add them up, you get 0.3066 atomic mass units. So this is just the 37 nucleons all added up by themselves. When you put them all together in the nucleus, they lose this much energy, 317.07 mega electron volts divided by 931 mega electron volts per U equals 0.3406. And so then we subtract 37.3066 minus the mass that we lost. And the mass of that nucleus, if I could write the number down correctly, 36.966 atomic mass units. So calculate the mass by itself. That's not the answer. This is the answer. Calculate the mass by itself, 37. Subtract the binding energy. But first you have to convert the binding energy to atomic mass units by just dividing. The binding energy per nucleon is important because it allows us to compare the different nuclei. If we were to plot everything out with all of our nuclei based on the mass numbers, you would get a graph that looks something like this, right? So this is the total number of protons and neutrons, the mass number. Okay? And then this is the binding energy per nucleon. Notice that the binding energy starts out really small and jumps up a bunch as it gets closer and closer to iron 56. And then the binding energy starts to go back down after that. So remember, the more binding energy, the more stable the nucleus. So the greatest binding energy on this curve is this iron isotope. That iron isotope is the most stable nucleus. Okay, and notice that it's around 8.8 mega electron volts. It's actually probably more like, that's a little closer to 9. So we're going to talk about this graph some as we go along, but it's important to recognize that the most stable nucleus is iron. There's lots of things that happen in the universe around you, as you will see, that relies on that being the most stable nucleus. And we're going to discuss that in the next few sections.